My dear student, I'm Mr. Kitwala from Educatiz. I will be with you in physics for Form 5. So, my dear student, welcome again for our discussion for our topic of wave for the subtopic of DC mechanical vibrations. So, on our today discussion, we are going to see about the velocity of vibrations of strings. Vibration of the velocity of vibration of a string. After finishing on defining the concept of damped oscillation, and we said that all of these damped oscillation are categorized into three parts. We have the underdamped, which passes through the Coulomb pulsation. Also, we have this critically damped. This is like the Kashoko. Also, we have this overdamped is like at the door that it returns to the current position very slowly. Now, it is a time to go and look this vibration, the velocity of vibration of a string. As we see, our statement say that, my dear student, the expression for the velocity of mechanical vibration, for instance, this vibrating a string, can be derived using the method of dimensional analysis. Kwa hizi expression za hizi velocity of mechanical velocity of the expression for the velocity of mechanical vibration, for instance, vibrating a system, can be derived using the method of dimensional analysis. Hizi zinabini derived kwa kutumia can be derived kwa kutumia hizi dimensional analysis. Kwa hiyo tunazitengeneza hizi kwa kutumia dimensional analysis, my dear student. So experiments show that the physical quantity that determine the velocity of this vibration on the string attention in the string. Kwa hii concept inajaribu kuelezea kuwa tunakuwa tunapata yule velocity of the vibration on the string kwa kuhusisha attention of the string, and also it is the linear density ambayo tunaita linear mass density ambayo tunaita ni mass per unit length. Kwa hiyo tuweze kupata velocity ya vibration ya ile string, lazima tuweze kuhusisha hivi vitu viwili, the tension of the string and also the mass density au tunaita ni mass per unit length, ni mass per unit length. Therefore, the velocity V can be obtained by the method of dimensions as it follows. Kwa hiyo tuweze kumpata huyu velocity, lazima tuweze kutumia njia ya dimensions. We should use the dimensions, my dear students, as it is shown here that the velocity is direct proportional to the tension times the linear mass density, ambayo sakuwa ni V direct proportion to them tension exponent A, this is a constant, times the linear mass density, which have the exponent which is equal to B. After there we should reduce this proportion. Tutajaribu kumwondoa yule proportion kwa kuweka constant ambaye ni K. Kwa ukishaweka constant ambaye ni K, you should obtain that this velocity must be equal to K times the tension exponent A, then we times by the coefficient by this coefficient, the linear mass density exponent this B, my lovely students. So where K is the dimensionless constant, lakini tunajua kabisa kwamba huyu K ana imply the dimension constant, kwa sababu huyu ni constant, ni dimensionless. It means ukiintroduce dimension pala atakuwa ni sawa na 1, my lovely students. So the dimension of V at T and mu can be written at this one. So in order to express this velocity at T and also mu, we should use their dimension. Kwa tuta express kwa kutumia dimension zake, kama tunavyoona kwamba huyu V dimension wake ni L T exponent -1, while this tension, this T, it is dimension is M L T exponent -2, while this linear mass density ambayo ni mass per unit length atakuwa dimension yake ni ml exponent negative 1 respect. Kwa huyu hapa atakuwa ni wa huyu wa kwanza, na huyu tension atakuwa ni huyu, and also this mu atakuwa ni huyu dimension wake, as we have been told, my dear student. So thus, by the method of dimension analysis, equation number 80.1 can be written at this one. Kwa sasa kwa kutumia method ya dimension, this equation here number 80.1, it can be expressed at this one. Kwa tutasubstitute sasa kwamba v is equal to k alafu mu t mu power a power b. Now if the k have the dimensions kwamba ni sawa na moja. Kwa hiyo ukiapply ukisubstitute pale dimension zake ya volume ya v ambayo ni velocity atakuwa ni m exponent 0 l power 1 alafu t power negative 1 ambayo ni sawa na m power a plus b, then l power a plus b, then t a minus b, then t exponent negative 2a, as we seen here, my lovely students. So solving for the dimension, let us take a comparison for the dimensions. Kwa tachukua m power 0 ni sawa na m power a plus b, but in form 2 we have been taught that if we have the same base, their exponent must be at the same. Kwa tutasema kumbe 0 ni sawa na a plus b. Kwa equation wa kwanza yule. For L also, L power 1 must be equal to L power negative, L power 1 is equal to L power a minus b. Because we have the same base, now we should equate their exponent. Kwa tukiequate exponent tutapata kumbe 1 is equal to a minus b, my dear students. And after there we should go for t, because we have t here. The t are found on the left side, which is t power negative 1 might be equal to t power negative 2a. Tukiequate pale tutapata kumbe we have the same base. We have the same base, kumbe wale exponent wenyewe wataweza kufanana. Kwa negative 1 ni sawa na negative 2a. Mwisho wa siku utakancel a, atakuwa ni half. Baada ya hapo tutakuja kwenye equation zingine ambazo tulikuwa tumesha prepare kwamba a plus b is equal to 0, tusubstitute thamani ya a ambayo ni ya half. Mwisho wa siku tutapata kumbe a b na mwenyewe atakuwa ni sawa na negative half. So after there we should, if we solve, we should obtain that the a must be equal to a half and b is equal to negative a half, my dear students. So substituting the value, baada ya kupata sasa tujaribu kwenda kusubstitute kwenye equation number 80 power 1, 80.1. Kwa tukisubstitute pale tutapata kumbe v is equal to the constant times the radical of the tension divided by the linear mass density. Kwa atakuwa ni equation number 3 for our topic number 80, my lovely students. So the equation this equation here show that the velocity of vibration is independent of the frequency of the vibration. Kwa hii equation sasa inajaribu kuelezea, kutupa overview ya kwanza kwamba inajaribu kuonyesha kwamba huyu vibration ya waves anakuwa hategemei frequency of the vibration, doesn't depend on the frequency of the vibrations. You should be asked some conceptual questions. What is how this equation show? What is the meaning of this equation? You will be asked as the conceptual questions. Kwa hii formula inakuwa ina maana gani? Mwambie kwamba hii equation ina imply kuwa your velocity of the vibration is independent with the meaning with the frequency of the vibration, my lovely students. So the velocity of the vibration is determined by the mechanical properties of the medium. We use mechanical properties of the medium so as to identify the velocity of the vibration, so as to determine or identify the velocity of the vibration of the vibration, my dear student. So experimentally, we should say that this k must be equals to 1. Then 80.3 can be written at this one. Kwa kama k atakuwa ni sawa na moja, basi huyo velocity of vibration atakuwa ni sawa na radical tension divided by mu, tension divided by the linear mass density, my lovely students. So this will be our equation number 4 for our topic number 80. Therefore, the velocity of mechanical vibration is equal to the square root of the tension per linear mass density. Kwa hiyo tutamwambia sasa kwamba huyu velocity wa mechanical vibration hatakuwa ni sawasawa na square root, must be equal to the square root of the tension per linear mass density. Kwa hiyo tutaulizwa pale kwamba hii equation ina maana gani. Tutamwambia kwamba equation yetu ya velocity of vibration must be equals to the square root of the tension divided by the linear mass density, my dear students. So by saying that, let us stop here. We could turn back and proceed with our discussion, my dear students.